let's talk about, this is something you have seen Dr. Matsumura talked about, but he didn't really call them by this name. Symplectic quotients. They're also known as Marsden-Weinstein. And to be completely fair, it should really be Meyer reduction. So when one proves the classical proof of Dilzon's theorem uses symplectic quotients, and I thought it's time to at least state the theorem. So this is Marsden-Weinstein Meyer. Early 1970s. Suppose we have a Hamiltonian action let's just say proper of a Lie group K on a manifold omega with equivariant moment map mu suppose further 0 is a regular value of mu of the moment map, then, well, mu inverse of 0 is a submanifold. And action of K on mu inverse of 0 is locally free. So let me remind you what this means. So if you like, there is a hyperlink. You press on it and it says, for any x in mu inverse of 0, the stabilizer is zero-dimensional. Right? So notice what that says. I assume that my action is proper. I'm giving you a version of it. Oftentimes it's stated for compact Lie groups, but you don't really need compactness of the group. You just need the properness of the action. Then the stabilizers are all compact because the action is proper. If you like, take it as a definition. And zero-dimensional compact manifolds are easy to classify. There are finitely many points. So it just says that the stabilizer of every point is finite. Moreover, for any point in mu inverse of 0, the kernel, well, if I have a submanifold in a symplectic manifold and I restrict the symplectic form to it, it may or may not be symplectic. Right? You've seen examples of isotropic submanifolds, or at least isotropic subspaces. You restrict the symplectic form, it's identically 0. So the restriction will have the kernel. And so let me be a bit more careful. So I restrict it at a particular point. So I restrict it to the tangent space, to mu inverse of 0. And the claim is this is the tangent space to the orbit. Right? So you have this submanifold, and you have a form. You restricted it, and it's degenerate. And it's degenerate in the directions of the orbits. Well, how do you get something non-degenerate? Divide out by the group action, you kill those directions. right? And the form is invariant, right? So you have a 2 form on the manifold with essentially a free action of a group, right? So you can push it down to the quotient. Hence, omega descends to a non-degenerate closed 2 form. Let me call it omega naught on the quotient. Let me denote the quotient 2 slashes and low 0 here. So this by definition is mu inverse of 0 mod k. And I'm going to be a little vague about what it means to divide out by k, or I can be very concrete, you just divide out by k. Then, well, the action is not quite free, so you get these finite quotient singularities. You can think there is a way to make sense of these forms on things that are not quite manifolds, they're orbifolds with finite quotient singularities. So this is there's actually more to this statement because usually people are also interested in dynamics. So there is usually a Hamiltonian floating around, which is invariant. You restrict to the level set. It turns out that the flow of this Hamiltonian has to preserve. If your function on M is k invariant, its flow will preserve this level set. And it's equivariant. Because the Hamiltonian is invariant, the flow is going to be equivariant, so it descends to a flow in the quotient here. And then you can take the function restricted to the 0 level set, push it down, compute the Hamiltonian with respect to this form, compute the vector field with respect to this form, and look at the flow. It's the one you started out with. So I'm not writing it down because we won't need it. There is a sort of a corollary. And I'm putting in quotation marks because it doesn't directly follow from this. Suppose, in addition, there is an action, proper Hamiltonian action of a Lie group H on M omega with moment map I don't know, mu H from M to H dual. I hope you can tell the difference between H's and K's, right? So for the what Dr. Matsumura did last time, he essentially applied this theorem in the particular case where M was C to the appropriate power, and the K was the really what he called, I think he called it G, right? You call it G? The kernel of the map, right? And he carried out this construction, and he got a new manifold, which was, by this theorem, symplectic. But there was another group action floating around. So it turns out that there's actually, if you start out with another action on this manifold, you can push it down. Actions of K and H commute. And mu H are, let's say, K cross H. So mu is H invariant. This is and mu is H invariant. So not equivariant, just preserved in the nose. Then H preserves, H acts on mu inverse of 0. Hence, on this level, this reduced space. Finally, the action of H on this reduced space with its reduced symplectic form is Hamiltonian. With moment map well, I don't know what to call it, mu h bar tilde. Obtained by restricting mu h to mu inverse of 0 and pushing it down. And I guess I should say mu h is k invariant. Let me just put it explicitly in as a hypothesis. So that tells you that if you started out with Cn and you picked a subtorus of the big torus, Tn, you carried out the reduction, then the quotient will act. You can think of it as a complementary torus. So example, M is C big N, K as a subtorus, H is isomorphic to Tn mod K, i.e. I'm splitting Tn as K cross H. I guess this is an isomorphism rather than equality. Right? And I'm putting it as in quotation marks because it's not really an example. Because I'm not writing down any equations or telling you which action. Then Cn. Oh, one thing I should say, here I'm very careful about putting 0 for a regular value. But moment maps for torus actions are defined up to scalars. So exactly the same construction works at a different regular value. So if I look at this quotient is an H toric manifold. So you kill one action, and you have an action left over. And these theorems are the ones that tell you what to do. Tell you why this works. As long as C is a regular value. C of K moment map. So this is not really an example. Let me work out an actual example. Right? There is this apocryphal story about a professor being asked to give an example of a Lie group. And he said, you want an example of a Lie group? G is a Lie group. So this is not that much better. So let's take M to be R mod Z cross R cross C. Let's take omega to be d theta wedge dp. So theta lives here. It's a cyclic variable in the old terminology. In other words, it's defined up to modulo z plus, but d theta is globally defined. And then I have, I don't know, I think I need to stick in some normalizing constants. Let's say dx wedge dy. So z is x plus iy. And I put 1 over pi there. Then S1 cross S1 acts on M by, so remember S1s are R mod Z. Let's see. So I have a torus action, theta p x, well, Maybe I'll put z here. Z is x plus iy. So what does it do? Well, tau1 just translates. So let me emphasize that this is mod z. And p stays unchanged, and this is e to the 2 pi I tau 2 z rotations. So both actions are Hamiltonian, but let's compute. So let's look at the action of first S1. So far so good? I think this might be a bit more concrete than this. Who knows? So I'm just translating this vector field. So the induced vector field that we talked about, I don't remember when, but we did talk about it. The vector field induced by this action is just dd theta. Right? We're translating, moving things with constant speed, so it's dd theta. So let's hook it into our form. We get, well, let's see. I'm contracting dd theta with d theta. I get dp. And I don't get anything else, right? So the first moment map, let's call it mu1 of theta pz is p. The second action is also Hamiltonian. And the other moment map, well, if I rig my constants right, this is just norm z squared. Maybe plus constant, but let's not worry about it. Now fix C in the this is kind of weird, R1 dual, this is R, right? So let me take it this way. It's in the algebra of the first circle. Right, our moment map looks like it's real valued. It really takes values in the dual of the reals. But who can tell the difference? So I'm fixing a constant. Let's see, everything is a regular value, right? Because my moment map is just a projection. And indeed, if I look at mu1 inverse of c, I get what? Theta cz. Theta z is in S R mod z plus c. Right? So that's this level set, the analog of mu inverse of 0. And let's see, and mu1 inverse of c mod S1. Well, let's see, what could that be? What's the orbit space here? I'm just trying. It's just C, right? I'm dividing it circle cross C, and I'm dividing out by the circle action, so I just get C. Should we check what the reduced symplectic form is? Right? You take this form, you restrict it to this set. This guy is completely 0. So you get this 2 form on a 3 manifold. Well, two forms on 3 manifolds have to be degenerate. The kernel is exactly the theta directions. And so omega naught here is 1 over pi dx wedge dy. And if you look at the moment map, well, what do? You take the moment map, the mu2, you restrict it to this level set. Well, it doesn't depend on the variable we divided out. And induced moment map. Mu2 tilde of z is, so it looks like we didn't do anything. So an example like this probably goes back to Jacobi, 1800s, elimination of nodes. But I haven't consulted it. So here's another example. So M is as before. Omega is as before. And I want to look at consider the action of H, which are tau 1, tau 2 in S1 cross S1. And I want tau 1 to be minus tau 2. So this is sort of the anti-diagonal. Moment map for this action, for the of H is, well, let's see. I have to is, how do you see what the moment map is? You plug in the induced vector field, and it's going to be something like dd theta still, but then there's another piece coming out from the action in the second factor, and we're rotating in the opposite direction. So when you rotate in the opposite direction, the sign in the moment map flips. So is mu of theta pz, it's going to be p minus norm z squared. Willing to believe that? Okay, so what's mu inverse of C? Well, it's theta p and z such that p minus norm z squared equals C, which I can rewrite as theta. Well, I know what p is, and z. So let's try to understand what the quotient is. I guess that's not too hard to understand. Well, let's see. If I'm writing it this way, this is really identifying it with R mod z cross C. Right? The p variable is completely determined by z, by the values of z. I'm looking at the graph. Right? This is really a graph over R cross z. R mod z cross C. So it is that. So you could see that if I kill the circle action, well, I have to be a little bit careful. What's my circle action? It rotates this guy in one direction, rotates this in the opposite direction. Well, it's one of those associated bundles over a point, also known as a vector space. Right? It's unusual, but not unheard of, to have a vector space to be defined as a vector bundle over a point. And here is an example. Right? So this is really C. Or I guess I should say omega C. What's the reduced form? Well, let me show you one trick. If I've done a bunch of identifications, and God knows what happened to the form. Well, I guess there are a few people in the audience who also know what happened to the form, but certainly known to more than just God. Let's be a bit more careful. Consider the following embedding. I can send W. I'm using a different letter because it's a different C. Where can I send it? I can send it to 1, C plus norm W squared and W. Right? And notice what I've done. I have some big manifold, 3-dimensional manifold. This is mu inverse of C. And I'm taking a copy of the complex line, and I'm embedding it somehow. Well, by this formula. And notice that I put the first variable to be exactly 1. Right? So that means every orbit is going to intersect at an exactly 1 point. These are S1 orbits. Right? Because my action is rotate here and rotate there. Right? My action is not just rotate here. I'm also acting here. But so I of C intersects every orbit in exactly 1 point. So if I compose, right, this is a submersion. So the composite is a diffeomorphism. Right? So it might be, this is really what we've done here. That's what, sorry. This is what's really being done here, but more rigorously, with a bit less hand waving. Okay, so we know this is the orbit space. Let's compute the symplectic form. Well, that's easy to do. You just take the form here and pull it back. So omega C is I star of d theta wedge dp plus 1 over pi dx wedge dx dy. And let's see. dp, I get some complicated expression. Well, not complicated. I have to differentiate some quadratic function. But theta is constant, so this term drops out. So this is just 1 over pi, I don't know, dx wedge dy. So w again is x plus iy. So we're again, the reason I wanted to work this example out is to show you that, this is easy. But you tweak things a tiny bit, and these reduced spaces get a little bit more complicated. Or they begin to look more complicated. And then you could check what happened to the moment maps. You see there is an action of the complementary torus left over. You have pick one. For example, right, my H is sort of like this. Here's S1, here's S1, here's H. Right? So you can pick this as a complementary torus. And then you get the old moment map back. But, so if you feel inspired, you can always tack on another C, right? And look at the diagonal action. So here's an exercise. M is R cross R mod Z cross S1 cross C cross C. So the form is d theta wedge dp plus summation j from 1 to 2, 1 over pi dxj wedge dyj. H Let me just write down the moment map that I want you to use, and then you can figure out the torus action. Right, moment maps. I'm going to write down the periodic Hamiltonian. Z1, Z2. I want it to be P minus norm Z1 squared plus norm Z2 squared plus some constant. So compute. Sorry? And the second one should be squared as well. Otherwise, it's not really a moment map. Or my Hamiltonian is scaled incorrectly. Right? Norm Z1. Yes? They're actually symplectomorphic. Equivariant, it's the same C. But I just picked a more complicated example. So what I'm trying to show by these examples is that if this was sort of, this is the trivial example, if you like. So you could see, so that people could see what the theorem says. And this is what happens in real life. Right? This is sort of the warm-up example for something that's in real life. This is slightly harder, right? Actually, what I should have done is let me fix this example. Let's live a little. Let's do the reduction with respect to S1 cross S1. Since I'm making these examples as a lecture, I realized that I should have put this one in. So this is a map into R2. It's a 2 torus action. So the reduced space should be the symplectic quotient. Let's do a quick count of dimensions. I have a function taking values of a vector space of dimension something, k. I take the preimage of 0 that cuts down the dimension by so this is dimension m minus dimension k. And then we divide out by the k action. The stabilizers are 0-dimensional, so that drops the dimension by dimension of the group again. So we decrease the number of dimensions by twice the dimension of the group. Right? So in the example I have erased, we started with a 4-manifold and got a surface. In this example, we started with a 4-manifold and got a surface. In this case, we're starting with a 6-manifold. We're still getting the surface.
Is symplectic quotient going to be connected?
Only if the 0 level set is connected. Doesn't have to be. Sorry?
So in general, maybe not.
In general, maybe not. Right? If M is, if this moment map is proper, if the moment map itself is proper, or you probably need the norm square of the moment map to be proper, then you'll get connectedness. I have to be a little, sorry, let me take this back. I keep thinking about compact V groups. For non-compact V groups, I have no idea. But there is a theorem of Kerwin that says that if the norm square of this map, put some invariant metric on this guy, which you can if the group is compact. And look at the norm square of this. then it's sort of minimally degenerate Morse-bot function. It's not really Morse-bot. And you can use Morse theory to prove connectedness of the level set. And there are also some examples where M is not compact, mu is not proper. Nonetheless, you get something connected. And the example I have in mind is take a symplectic representation of a compact Lie group. The zero level set is actually kind of easy to see that it's connected because the moment map is going to be quadratic and homogeneous, so the level set is actually contractible. But the claim is that mu inverse of any C is connected. And these guys are usually not proper, right? So the example, for example, mu of right? It's this quadratic. The claim is that all its level sets are connected. Right? This is just this is an S1 moment map. If you have something more complicated, you get an intersection of a bunch of real quadratics. Who knows what they're going to be? I claim they're all connected. You can't use Morse theory directly. But if you buy me a beer, I'll tell you how to do it. But I'm sorry, I digressed. Other questions? So I figured we have about half an hour so I can prove this theorem. And that might actually be educational. OK. So proof of Marsden-Weinstein-Meyer. So let me paste for some of the sins from yesterday and actually define things properly. So let's start with a symplectic vector space. And so suppose U in W a subspace. I talked yesterday about symplectic perpendiculars, but I never actually defined it. And the people who didn't know what these symbols stand for were too shy to ask. But I suspect that set is non-empty. Right? So what's this? It's all W's in W so that omega UW is 0 for all U in U. Right? So that might look familiar. Note, here's another description of UW. Remember we have this map omega sharp that goes from W to W dual that takes W to omega of W dot. And the claim is this is p-image of the annihilator, where U naught is all the linear functionals, all restricted to U is identically 0. Right? So the people who know about symplectic perps probably know this fact as well. But notice what it buys me. The fact that I would need this fact, but another thing you can get out of this. Sorry, let me step back one sentence. Rewind that sentence. If you look at these definitions, this is not like in Riemannian geometry where the perpendiculars are complementary. Right? U is always perpendicular to itself. So you might get something that's U perp need not be disjoint from U. So it's not clear what its dimension is. This tells you what the dimension is. Because you can compute the dimension of the annihilator. It is of complementary dimension. And the other thing you could prove using these dimension counts that if you take perp twice, you get U back. Right? I'm strongly using the fact that W is finite dimensional here. I didn't say it, but I'm using it. Right? Because otherwise you just get an inclusion, not the equality. But I don't want to do infinite dimensional symplectic geometry today. Or maybe tomorrow either. All right. So the next thing that I need is the following lemma. And that sort of goes into the heart of the matter. So I have my moment map. So let mu from M to K du be as above. And the claim is for any x in M, for any big X in Lie algebra, and hopefully you can tell the two x's apart, for any vector tangent to M, we have the following relation. I can take the differential of the moment map at x. Right? It's a vector valued function. Take the differential, it's vector valued. Feed v into it. It takes values in the dual of the Lie algebra. So I can pair it with x. And the claim is this is omega at the point x. The induced vector field and v. I'm sure this lemma is somewhere in Anakonish's book on symplectic geometry and a whole bunch of other places. And I think it is in the original paper of Marsden and Weinstein. But it's a little hard to get hold of because they published it in some Polish journal. The Meyer's paper is in conference proceedings. So, okay, so let's do the proof. Oh yes, and if you look at that paper, you could, Marsden and Weinstein called this Smale's procedure. But I don't think anybody else ever called it that since. There are papers of Smale in the late 60s in the Invenciones where something like this is done, but for abelian groups. Okay, so observation is basically this formula is true that because for any x in K, this map from K du to R is linear. Right? Double duals. So let's see. What's this? This is the contraction. So I'm going to try to compute this side and get that out. This is the contraction of the induced vector field with omega at the point x on V. This is d. By definition of the Hamiltonian vector field, it's d of the moment map paired with x at the point x applied to V. And now all I need to do is apply the chain rule. So this is d. Right, I don't know how to write x as a function, but that's what I'm doing. And this is this function paired with, composed with d mu of x on V. But what does it mean to apply this and then that? It means you plug this guy into this slot. So you get d mu x on V paired with x. And that's the proof. So here's another lemma that will have two parts. So remember, the differential of the moment map takes values in the dual Lie algebra. So I can look at its image. So that's something that sits in K dual. And I can take its annihilator. Now this is a subspace of the Lie algebra. And the claim is, this is the Lie algebra. So this K low x is the Lie algebra of the stabilizer. So you can see that there is some relationship between this map being onto. Actually, it's easy to see, right? One is something irregular value. When the annihilator is 0, the annihilator is 0 by this part just tells you that this Lie algebra is 0, which is another way of saying it, the group is zero-dimensional. So this is really proves a piece. And the other one tells you what the kernel is. Now let's see, if x is a regular value, the kernel of the differential is the tangent space to the level set. And the claim is, this is the symplectic perpendicular to the tangent space to the orbit. So if you apply this little fact, or basically this says that if I take the symplectic form and restrict it to this set, the null directions are exactly the orbits. So it may not look like it, but I'm actually proving the theorem. Okay? So here's a proof. Easy fact. How do you recognize that something is in the Lie algebra of the stabilizer? Well, the induced vector field at the point x is 0. One direction is obvious, the other one maybe dimension count. Right, if something is in the stabilizer, then we cannot move x. You differentiate, you get the vector field vanish. The other way, you have to say something. Now, since omega is non-degenerate, the induced vector field at x is 0 if and only if for any v in the tangent space, if I stick it into the symplectic form and pair it with v, I get 0. So this is a clever but very, very cheap observation. But what's this thing? Well, we just computed that. Where did it go? It's over there. So let's put everything together. X is in the stabilizer of in the Lie algebra of the stabilizer. If and only if this side is 0, which means this side is 0. For all tangents vectors. And that says exactly, let's see. It just says that x has to annihilate the image of this differential. So that proves one. Maybe a little too fast. No? The proof of the second fact is equally fast. So suppose I have something in the kernel of the differential. Well, it's if I apply d mu x to v, I should get 0, right? But that means that if I pair with anything, I should get 0 for all vectors. But this is true by the first lemma if and only if, let's see, omega sub x, x m x v is 0 for all x. And this says, well, let's see, what's the collection of all these vectors as x varies over Lie algebra? That's the tangent space to the Lie group. It just says that v is in the perpendicular to the tangent space to the Lie group. So look at the image of d mu, of the differential at the point x. Right, so d mu x is a map from the tangent space to the manifold to the tangent space at mu of x to the duo of the Lie algebra, which is the duo of the Lie algebra. Right? It's a vector space valued map. So it makes sense, right? So the image of this, so another way of saying this is that image of d mu x is the annihilator of the stabilizer, right? Flip the annihilators. The image is being annihilated precisely by the. So you could see that you'll have trouble, sort of double trouble, if your action is not free at the point x. The image is not going to be onto, and you'll have a stabilizer. If you have non-trivial stabilizers, they're singular points of your moment map. So they're easy to detect. So lemma 3, something is a regular value of mu of the moment map if and only if for any points in the preimage the stabilizer, the Lie algebra of the stabilizer is 0. So in effect, we have this proved, but let me just recap it. Right, so this is this line. So this is lemma 3. If you're wondering which piece of the theorem I'm proving now. Right here, I'm assuming that 0 is a regular value, but it's really if and only if statement. So the moral of the story is whenever you have stabilizers, they're singular points. And if you go back to the models for torus actions in toric manifolds that I wrote down, you could see the singular values occurring exactly at points with non-zero stabilizers. Because the moment maps for the action of the torus on a vector space are quadratic, so they have singularities at 0. Okay. So eta is a regular value of mu if and only if what? For any x in mu inverse of eta, d mu x is onto. If and only if I look at the image and look at the annihilator, I get 0. So this is a little circle, and that's a big 0. If and only if, well, what we know what the annihilator is. So this is lemma 2 part. So let's prove the theorem. So suppose 0 is a regular value of mu. By lemma 3, the stabilizer is zero-dimensional, hence finite. That's because we're assuming that the action is proper. Or if you prefer, you might as well think of the group K as being compact. Right? Zero-dimensional subgroups of compact Lie groups are finite. Now, for any x in mu inverse of 0, the tangent space to mu inverse of 0 at this point x is the kernel of the differential. Right? That's the inverse function theorem of some sort. So lemma 2 part 2 tells you that if I look at the perp, what do I get? I get the tangent space to the orbit perp. Right? So what are these vectors? These are all the vectors that perpendicular to the tangent space, which turns out to be just, right, taking perps twice gives you the space back. And that tells you, so all the vectors perpendicular to all the tangent vectors are exactly the things in the orbit, but they happen to sit inside. So that just tells you exactly where your symplectic form is degenerate. If this were not a subspace, to compute the kernel of the restriction of the form to this level set, I would have to intersect the perp, right? So let me write it this way. The kernel of omega restricted to mu inverse of 0 at some point x is tangent space mu inverse of 0 perp intersect tangent space with mu inverse of 0. This is more or less by definition of the kernel of the restriction. But that's the tangent space to the orbit intersect the tangent space to the level set. And I guess at this point, the equivariance of the moment map kicks in. This is the orbits sit inside the level set. If my moment map was not equivariant, I would have to do something else. But I define them to be that way. So this essentially proves the whole theorem. Let me just assume for simplicity. So we won't have to muck around with orbitals. That the stabilizers are all true for all x and mu inverse of 0. Then the level set is a principal K bundle. Then the orbit space is a nice manifold. The action is free and proper. And it's really a principal bundle. And we have a two-form here that's invariant and horizontal. And let's just say and basic. So let's call this map pi. All projections are called pi. So there exists unique omega naught, a two-form on mu inverse of 0 mod k, such that its pullback is omega. And since we killed exactly the directions where omega was degenerate, it's non-degenerate. Moreover, since kernel of omega restricted to mu inverse of 0 is k orbit are k orbit directions, are vertical directions, in the bundle omega naught is non-degenerate. Right. Looks like we've got everything. Are we done with the proof? Or at least this part. Right, the theorem itself, not the corollary. Or did I actually not do something? I just want to check if people can think and take notes at the same time, which is a cruel test. There's something I haven't actually proved. And since we have 4 minutes, I could give people time to see what I left out. Right? What did we want to prove? We wanted to prove this omega naught is a symplectic form. What did I prove? I proved that it's non-degenerate. What did I leave out? Closed. Okay. So should we prove that? Anybody sees why it should be closed? Well, let's compute. Well, I want to prove that this is 0. Let's pull it up. Right? If I have a submersion and I have a form that's 0, whose pullback is 0, then the form had to be 0 to begin with. Right? So if I can prove that this is 0, I'm done. Well, let's see. This is d of pi star of omega naught, which is d of omega restricted to mu inverse of 0, which is d omega restricted to mu inverse of 0, which is 0. Since pi is a submersion, d omega naught plus 0 as well. So maybe that's enough proofs for one lecture. I have about a page and a half left. Thank you.
Any questions?